Welcome back to the course Introduction to Green Process Engineering. Today we will explore the possibilities of producing plastics from renewable resources and whether they already play a role in our daily life. First, we need to know what is meant by bioplastics before we can have a look at the input materials. After this, I will discuss the most relevant industry example. Besides the massive plastic production and not yet fully implemented strategies for plastic recycling, the degradation of plastic is an issue. Plastic commodities often have a relatively short lifespan. If you think of any plastic packaging that you have in your caddy, its service life is really short, but at the same time it may stay in the environment for centuries. Here you can see some examples of decomposition times. For example, a leather shoe requires 40 years of decomposition. An aluminum can needs 250 years, but plastic bottles already require 450 years. By far the longest time is required for styrofoam, for which decomposition is indicated here as never. During the decomposition, microplastics are formed, which are not easily removed. Well-organized collection and recycling is needed besides the change to bio-based plastics. So what do we mean by bioplastics? The umbrella term bioplastics is often used to describe very different materials, and the terms bio-based, biodegradable, and compostable may be misleading. Bio-based plastics are fully or partially made from biological resources rather than fossil raw materials. They are not necessarily biodegradable or compostable. It is important to examine the full life cycle of bio-based plastics to ensure that they are beneficial to the environment beyond the reduction in use of fossil resources. This includes changes in land use. Biodegradable plastics biodegrade in certain conditions at their end of life. Compostable plastics, a subset of biodegradable ones, typically decompose in industrial composting facilities and first need to be collected. Polylactic acid, in short PLA, is by far the most prominent type of bioplastic. It is produced from cornstarch and sugarcane by microbial fermentation. It has gained attention for its biodegradability and application in packaging and single-use products. Research has also shown that PLA can be mechanically recycled. You already should know from a previous lecture that for mechanical recycling, pure input streams are needed. Hence, collection and sorting are an issue in this case. Another notable example is bio-based polyethylene, produced from bioethanol derived from sugarcane, which maintains a similar polymer structure to conventional polyethylene but originates from renewable biomass sources. Its biodegradability is certainly the same as for fossil-based polyethylene. Cellulose-based plastics can be used in applications ranging from packaging to industrial uses and hold promise for the environmental benefits due to their renewable origin. Bio-based composites, which are made by combining bio-based polymers with natural fibers, such as cellulose or plant-based fibers, not only retain the mechanical properties needed for various applications, but also potentially offer enhanced biodegradability compared to their petrochemical counterparts. To give an example, the use of fig fibers in combination with a natural resin has been shown to enhance the mechanical performance of composites while retaining environmental benefits. Glycerol and adipic acid are examples for bio-based monomers that are used to produce hyper-branched polyesters that serve as plasticizers for various applications. Overall, bio-based plastics are materials that offer environmentally friendly alternatives to conventional plastics. We will now have a look at one production path in a bit more detail. You can see here the production pathway of lactic acid from cornstarch. In the first step, corn kernels are processed to extract starch. This involves grinding the corn and subjecting it to steeping in water, followed by a separation of proteins and fibers from the starchy endosperm. The resulting cornstarch is used as the feedstock for the following microbial fermentation to lactic acid. The extracted cornstarch undergoes a hydrolysis process where it is converted into fermentable sugars, mainly glucose, using several enzymatic treatments. Within the fermentation process, monomeric sugars, here you see the example of glucose, is converted by microorganisms into optically pure lactic acid. I need to make a crucial point here. Lactic acid is also produced from fossil resources, but in that case not optically pure lactic acid, but the racemic mixture is present. However, only optically pure lactic acid can be used for further chemical polymerization to polylactic acid. After chemical polymerization, polylactic acid can be processed into various forms such as films, fibers, or molded products utilizing techniques such as extrusion, injection molding, and spinning. You have definitely already encountered objects made from polylactic acid. Just have a look at your lunchbox or your refill cup. If they are not made from glass or steel, they are most probably made from polylactic acid. This already brings me to the end of the course. Within this course, Professor Karin, Stana, Kleinschek and I gave you an overview of definitions when it comes to economies. You probably remember the term circular bioeconomy of water, but we also have defined subsystems such as the marine bioeconomy or the plant-based bioeconomy. We dealt with transition pathways for the different industry sectors, such as the chemical industry, and in the end we had a look at some examples, such as the pulp and paper industry and at new solvents, ending with the overview I gave in this video of bio-based plastics and the most relevant industry example. I hope you enjoyed the overall course and you got at least a glimpse of some relevant technologies and products that foster both the material and energy transition. With that, I would like to thank you for watching.